Hello everyone, my name is Samir Kumar Singh. Today we will discuss the week 12 tutorial and this is the last class of the this session this semester. Okay, so this is the contents of today's presentation, today's discussion session. Basically, firstly we will see the VER of the maximum ratio combining. Next we will go for the LMRT space-time clock code, and the last we will take few questions. Okay, and in last class basically we focus on the lab code that and there we will discuss the relay channel generation, SC combining techniques and EGC techniques, but can be calculated the BER of that codes. So to extend this class, then there we will see the best MRC schemes, LMRT codes, and last question session. Okay, so these before going to the code session, I'm giving just overview of the MRC schemes that will help you out. Okay, basically in MRC techniques, we consider the one transmit antenna and a receiver antenna. Basically, in this scenario, we have a one antenna transmit and antenna and receiving end. Okay, this is the okay. To so then output will be it look like that y is equal to hx plus n. H is denote the channel and return noise. Generally, noise is considered as additive and cohesion noise, and this is the representation of the y. It has n outputs because we have n channel at n antennas at receiver end. Okay, so we will get n outputs. So next h is the channels that are going from the 1 to n. Similarly, we have noise and noise terms. Okay, so that is the representation of this equation. Okay, so what is the advantage of the MRC schemes? Basically, if we calculate overall effective SNR by using the MRC, we are getting the n times of an SNR. Okay, where I is going from the 1 to n. So overall, we are getting the that times of effective SNR. So these are the steps how can we generate the MRC diversity scheme in the MATLAB. How we can generate the the MRC schemes in the MATLAB code. Okay, so basically firstly we will these are the 5 steps. Then we divide. Firstly we generate the bits randomly in the form of +1 and -1. Basically it's a BPSK modulation. So our first task the generation of random bits. Next is the channel and white Gaussian noise, as we already discussed in the last class. So our prime focus to start this code, firstly we generate the we generate the input bits that will form another +1 -1. Next we will generate a channel, and third we will go for the noise. Okay, next after generating in this all these three terms, next multiply the bits mean the random bits that are in the form of 1 +1 and -1. Then we multiply the bits with the channel. Okay, and after that we will add the noise. It will look like that. Okay, this is the input bits, that's the channel, then we multiply both and generate the, and then after that we will add this term with the noise. Okay, it is an n. Next, after getting the y on the receiver end, so then on the receiver end select the receive part, equalize the received symbols per maximum ratio combining, that is the role of MRC. Okay, we will do the equalization the receivers and receive symbols. After doing this, we perform the hard decision decoding to decode. We will try to decode the receive symbol. Okay, actually we get the y not in the form of 1 -1, so we will try to decode it, and after that we will compare the input bits with undecoded bit, and from there we will count the error. Okay, so from there we can get the bit VER. So point is that now next we will repeat this step for the multiple SNRs values, because we have to plot the curve. Okay, so we will do it the multiple SNRs, and for in MATLAB we basically use the for loops for these terms. Okay, and then plot the simulated result. These are the differences that I have taken from this source. These all work. Okay, so now we will go on the MATLAB session. Okay, MATLAB code. So this is the code of the MRC schemes. So firstly, these three commands we use to write. We generally use the first the CLC. So CLC is used to clear the command window. Basically, this is the command window that is a workspace. So, okay, to clear the command window, we use the CLC. Next is the close all. Basically, it is used to close the all triggers. Okay, and okay, next is the clear all. A clear all is used to clear the workspace. Suppose these terms are showing in the workspace, you want to clear this space, you can type clear all. So you can see that your workspace is clear. As you type the clear all in command window, your workspace will be clear. Similarly, just you, if you want to see the value, then okay. Sorry, first we have to run this code. So we are running this, so we will wait for a few seconds. Okay, we will see this in up to 6 times. Okay, so suppose we want to check the uh, y. Okay, just type there y, and so you are getting lots of values of the y in the command window, or you want to clear this. So simply just type the CLC. When you type the CLC in your command window, your command window will be clear. Okay, so to clear the workspace, we will use clear all, and clear the command window we use the CLC. Okay, generally we always use these three code in initials. Okay, next, so what are the basic steps to for the MRC techniques? So our task is, firstly we will generate input bits in form of +1 -1, then channel, and then Gaussian wise. So you here, we consider that we have number of bits, it's 10 to the power 6. This is our okay. So, and for the run the for loop, we have taken the multiple SNR values that is going from the 0 to 25. Okay, and that are in a DV. Okay, we will discuss about the for loop later. Okay, so first task is generate input bits. So to generate input bits in randomly in form of 0 and 1, we are using the rand command. Okay, so we are, suppose here you enter that k is equal to 2. Okay, and you are doing, you're using expand 1 comma k. When you run it in this in command window, you are getting that you are getting two values. Okay, but this is 0.2, this is a 0.1, but you want in the form of 0 or 1, then you just use the 0 greater than symbol and compare 0.1. This means when your value come greater than the 0.15, it will consider as 1, and when it would be less than 0.5, it will become 0. Okay, just look at now. Okay, rand 1 comma k greater than 0.5. Now we are getting a 1 1 because these two values are, when we are getting value greater than 0.5, that's why this is coming 1 1. Okay, so we are here we here get the input in form of 0 and 1. Next, to get basically what is our task, we have to generate +1 and -1 in the form of input in the +1 -1, but here we are getting in the input in the form of 0 and 1. So we apply this equation. From there we will get our input in the form of +1 and -1. Here you can see that matrix is very well. All the inputs is coming in the form of +1 and -1. Okay, sorry, I just taken LMRT code, but firstly we will discuss MRC. Okay, so all the theory is same. We generated our input bits. Okay, just look at it. The first task was to generate the input bits in form of +1 -1. So here we will get our input bit. Okay, next in the receiver side we are considering the two antennas. Okay, that is a 1 and 2. That is the SNR values. This is going from the 0 to 35. We will run a loop for the multiple SNR values. Okay, so these are the for loops. So okay, we have the two antennas at receiver side. Okay, so we run the two loops for the receiver antenna 1 and receiver antenna 2, and similarly next we are calculating the VER for the multiple SNRs. To represent this we are using the for loop. Okay, first okay, so then we generated input bits. Now we will generate the noise and channel. To generate the noise we use a function of random. This is showing the real parts and that is the imaginary. Okay, here NRX is the number of antennas. Okay, JJ is going from the 1 to 2 because length of our antenna is size of antenna is this matrix is 2. So by using this we can generate a noise and we can generate a channel. So first step is completed. We get the input bits, noise and channel. Okay, next we will do the addition of the channel noise. Okay, so that is the count function we are using for this. Okay, so this is a sh and this is the s input bits h and noise. So there we are get the our output symbol in form of y. Okay, we have two antennas, that's why we are getting a 2 cross 10 to power 6 size of matrix. Okay, next we apply the equalization. As we see there, after getting y we will apply the we apply the equalization on the receiver symbol. Okay, so we apply the equalization, and for this we multiply the our input bits our output bit with the conjugate h and divide with the distance. Okay, now we have the y hat. After the equalization we get the y hat. Okay, so what is our next step? You can see that next we will apply the hard decision decoding. We apply the decoding and try to count the bit errors. So to decode we are for the comparison we are taking the 0 as a reference. Basically you can see that y hat, you are if you see the y hat and which see the focus on the real parts. First pass is coming 0.99, next is coming 0.9930, and third term is a minus ka 0.97, fourth is a minus 1.0116. So you are seeing, you can observe that there are lots of variation. Okay, but what we transmit a 1 and -1, so we compare our input bit input hat. So for that we taking the reference as a 0. Whenever we are getting our real part of the y hat is greater than 0, we consider this as a 1, and when we are getting less than 0 we consider this as the -1. Okay, if it's match then there is a no error. If it doesn't match, it means we are getting error. Okay, so and this value will store in the this function, this variable. Okay, so there you can see that so here we compared and count this basically we give the counts of the number of errors, and the column 1 showing the highest we are. And if you observe, you see, if you if you see the column 1 and compare with the 36, and 36 you are just getting 72 and 0, but in column 1 we are getting very high values, because as we are going to in the right side we are increasing our SNR values. That's why as we increase the SNR our PR will be reduces. That's the reason behind this. Okay, so in this variable we stores the number of errors. Okay, now to calculate the bit error rate, next to calculate the BER we divide the number of errors with the total number of bits. So basically we are considered 10 to power 6 bits, and that is the error. So after that we are getting the simulated VR that is coming on this form. Okay, so okay, basically initially we consider the SNR in the dB to calculate in linear function. We are using this. Okay, these are the basic terms for the comparison purpose. We are using that theoretically we calculated with VR of the receiver one antenna theoretically, and here we calculated we theoretically we are for the receiver antenna 2. Okay, next task is now we calculate our VR. Next task is the plotting. So for this we are plotting in the semi-log paper. Okay, in the x-axis we consider SNR, and the y-axis we are considering the BER of the. Okay, in there we are consider the BER of the receiver first antenna. This is the second antenna. Okay, that is showing a simulated BER, the typical BER. Now we will plot it. We plot it. So that this is the plot of the BER of or the BPSK modulation with MRC delay channel. Okay, this is the for the first two curve for the one antennas. This is for the second. That is the advantage of this MRC, and where we consider we reduce or BR has been reduced this. Okay, so now we will next again we will go in the PPT. Okay, so we calculate the BR of the MRC diversity schemes. That is the code we already discussed. That, and that is the final curve. Okay, next we will discuss LMRT STVC codes. Okay, LMRT STVC is known as space-time block code. We already learned the SC scheme, GC scheme, MRC now, and here we will discuss the LMRT STVC code. Okay, so this is the explanation of the short overview of the STVC code, LMRT STVC codes. For okay, so there we consider that we have a transmission sequence. We have to transmit this sequence. Okay, so in generally what we will do, normally we transmit x1 with x1 is the first time slot and x2 is in the second time slot. Okay, but in the LMRT code we will send x1 sorry we will send x1 and x2 in the first time by using the first and second antenna. Or in first time slot we will send x1 and x2 by using the first and second antenna, while in second slot we will send minus x2 star and x1 star from the first and second antenna. This will be sent from first, and that will be sent from the second antenna. Okay, so mainly we are making a group of two symbols. Okay, so in first slot we are making we have made the group of the x1 x2. In second slot we make the group of minus x2 and x1, minus x2 stars and x1 star. And so mainly we are making a group of the two symbol and still using two time slot to send it, as there is no change in the data rate. This mechanism we are using in the LMRT STVC code. Okay, this is the mathematical representation. In the first time slot we are sending the x1 and x2, that is the channel for the both, while in the second time slot we are sending the minus x2 star and x1 stars from antenna 1 and antenna 2. So we have to now we will calculate a BER of the LMRT code. Okay, this is the basic steps that we follow to calculate the BER. Okay, so simply we firstly generate the bits in the form of +1 and -1. Okay, next we will make a group of two symbols. Here we will get inputs. Okay, after that code it for the LMRT space-time code, then multiply this with the channel and the add noise. Next we generate the channel and noise. Then as we get the output or y output, then on receiver end we will apply the equalization. After that we will try to decode it. So we will perform the perform the hard decision decoding. Okay, hard decision decoding and count the bit errors. And similarly the last code, we repeat this step for the multiple SNR values and plot the simulated result. Okay, this is the code for the Alamati STBC code. So we will go MATLAB. Okay, that is the code. So that is written there, already written there. These are three basic commands: CLC, close one, and clear. Next, we consider the number of bits is 10 to power 6. That is our SNR values. That is going from the 0 to 25. Basically, it is all in the dB. Okay. To writing we are writing the for loop. Okay. That is running from the 1 to length of the EB and not DB. We have basically there it is that the length of the EB and not DB is 26. So our first task is generate the input. So to generate the random inputs in form of 0, 1, we are using the rand function compared with the 0.5. By this we can get our input bits. Okay. Next is what is task? We will represent 0 as a -1 and 1 as a 0. Okay, we apply the BPSK modulation, so you can do this from there. Next, we will see the Alamati STBC code. So here we generated a matrix a size of 2 10 to power 6. That's that basically that is looking at. Firstly, we run the code. Okay, so initially it's okay. We see the S code. You can see there. Okay, initially its size of this S code is a 2 into 10 to power 6. Initially it will be 0 0 0 0. Okay, initially it will be 0, and if you take this, here we are using a reshape function and cron function to manage the to manage the size of the matrix. Okay, next task is to generate the H channel. Okay, to generate a channel, we basically we consider that our channel is the relay. Okay, so to generate a relay channel, we can directly use this equation. Okay, next we get the H. So basically we have the two. So to repeating the same we have the two symbols, so repeating the same channel for the two symbols. That is for the first. Okay, from there we get the H mod. Next we will generate the noise, and here we are generating the Guide Gaussian noise that having the 0 dB variance. Next task is the y is equal to, generally we did the y is equal to hx plus n. So again we are trying to get our output y. So that is the our h mod. S code is the one in Alamati inputs, and that is the noise. Okay, and loop is running from the 0 to 25. So we get the y. We get the y. Okay, here we are doing the reshaping. Okay, so suppose you are getting this, and here you are getting the on this one. After getting the y, we apply the equalization, and in this code we are doing this. We are doing the equalization by using this matrix. Again, here we are generating the h in this function, and the size of this 2 to 10 to the power 6. And again we are using a reshape cron functions, and we get the HUK. Okay, To calculate the power of H, we multiply with the conjugate of the HUQ with the HUQ. Okay, HUQ. Now we are getting the Y hat. Okay, this form H1Y1 H2Y2 star. Similarly, H2Y1 minus H2Y1 stars. Okay, after that we apply the decoding and receive our hard decision decoding. Again, we are comparing the Y hat with the 0 as we get the greater than 0. Okay, real part, if your real part coming the greater than 0 0, then we consider this 1, otherwise minus 1. Okay, so here we get the input at, okay, that is coming in the form of 1 and 0, and next we will calculate the number of errors. We can compare our input bits with the input hat, and at the differences will count, and here we are getting the number of errors from the multiple SNRs value, that SNRs varying from the 0 to 25. Okay, okay, this is the simulated VR. So simulated VR is basically number of errors and upon total bits. Total bits is 1046. So again we are getting the simulated VR for the multiple SNRs values. There we are considering the 26 values. So that is stored in this matrix. Okay, again convert the SNR in linear. We are using this function. Here we calculate the theoretical BAR, MRC, BR of MRC, and LMRT codes. After getting all these three, we plot the whole function, the derivative function. Okay, so this is the PR of the BPSK modulation schemes with the LMRT STBC codes. Okay, thank you. Okay, this is the code of the LMRT STBC codes. So already discussed in the MATLAB. Okay, okay, that now we will see the question and session. We go for the question session. Okay, there in this section we consider I take the 5 questions. Okay, so question number 1 is the which of the following is our benefits for the MIMO system. You have to tell the advantages of the MIMO system. Option is the increased capacity, diversity benefits. C part is the both A and B. Then D is none of the above. So please let me know which option is true. Take your time. It's very simple question. We have just let me know which option is the true for which. What are the advantages of the MIMO system? What are the benefits? MIMO system increased capacity. It gave us diversity benefits. Both are true. Okay, so as we know that the advantage of the benefits and the advantage of MIMO is we are getting the various advantage of the MIMO system. MIMO is known as the multiple input and multiple output puts. If you try to um, uh, understand the last LMRT code and the MRC GC, here we are taking the one antenna transmitter and multiple antenna receiver, and but in the MIMO we can consider the multiple antennas transmitter and multiple antenna receiver. So basically with this is a scenario increased capacity and we are getting the diversity benefits. So C part is the right answer because both A and B we are getting with the MIMO. So C is the right option. Now question number 2 is consider a MIMO system in which the channel transfer matrix H is known. Okay, H is known. Which of the following method is best for the capacity analysis if H is not a square matrix? Suppose again I'm repeating. We have a MIMO system and we have We have a channel transfer matrix H that is known, but this is not a square matrix. The pitch method is the best for the capacity analysis. Options are max matrix inversion, next is singular value decomposition, matrix conjugate, matrix transpose. Please comment. Okay, if you have better knowledge of H, okay, so on channel especially where H is not a square matrix, we will use the single value decomposition. The B part is the right. Next, the which of the following is the assumption made in the conventional MIMO system? Question number 3 is the which of the following is are assumption of made in the conventional MIMO system? The element of the channel transfer matrix are non-zero or zero mean complex Gaussian value. The noise elements are complex additive wide Gaussian with zero mean. The transmitted signal X are zero mean complex Gaussian values. These are all of them. Again, I am repeating, which of the following is assumptions made in the conventional MIMO system? Option A, the element of the channel transfer matrix are zero mean complex Gaussian values. The noise elements are the complex additive wide Gaussian with zero mean. Transmitted signal X are zero mean complex Gaussian value. These are all of them. So this all three is the right for the conventional MIMO system. Okay, the option D will be right. So for the question number 3, D option is the right. Conventional basically all the assumption has been taken in the conventional MIMO system. Next question is, which of the following is true regarding the power allocation in the MIMO system? Question, which of the following is true regarding the power allocation in the MIMO system? Option is channel with better SNR get higher power allocation. Channel with poorer SNR get higher allocation. Channel state information and a transmitter is required for the optimum power allocation. These are the 4 A and C. Which of the following is true regarding the power allocation in the MIMO system? Okay, this is the explanation of this question, and these are right. Basically, A and C is the correct answer for the correct strategy for the power allocation in the MIMO system. Basically, channel with better SNR get higher power allocation, and C is the CSI, channel state information and a transmitter is required for the optimum power allocation. Okay, if it is if we know the CSIT, then that is better. Optimum power allocation is a water filling solution that can only be obtained when CSIT is present. Next is water filling solution tells us to allocate more power to channels with higher SNR and less power to choose with a poorer SNR. Next question is, which of the best strategy for power allocation if all channel have a poor SNR? Question is, which is the best strategy for the power allocation if all channel have poor SNR? Scenario is all channels we are getting the poor SNR from the all channels. So how we can allocate our power? Allocation of power to the channel with the highest SNR and zero power to the other channel First option is allocation of the power to the channel with highest SNR and zero power to the other channel. Next is allocate equal power to all channel. See the both A and B, there is a none of them. So option is that right option. According to right, according to the allocation of the power to the channel with the highest SNR and zero power to the other channels. This is the explanation. If all channel have a poor SNR, the water filling solution lead us to allocate all power to the best channel and give zero power to the remaining channel. Thank you.